So factorize completely x cubed plus 10x squared plus 25x. So I've gone ahead and done it already, but the trick is to realize that we're just working with x's firstly. So to factorize x is easy. You're left with x squared plus 10x plus 25. And now looking at this quadratic, you just need to pick, open up two brackets and realize two numbers that multiply to make 25. And well, that's going to be, of course, 5 and 5, because that's the only combination. And we also realize that out of those two numbers, 5 plus 5 also makes 10. And that's it. This is fully factorized. Now, part B. Sketch the curve with this equation below. So that's the same one up here. Showing the coordinates of the points at which the curve cuts or touches the x-axis. Okay, so first things first, let's go ahead and understand what we're drawing. This is a cubic graph. So a cubic graph, and this is a positive cubic. Cubic graphs always start at the bottom, curve down and shoot upwards. A negative cubic starts from the top, curves up and then shoots downwards. So negative downwards, positive upwards. Okay, easy stuff really. So, and all we have to realize is that these x values here represent the points where the curve hits the x-axis. So let's have a little sketch. So just draw your graph like this, and just realize that our critical points is going to be when x equals 0 and x equals -5. When you've got two values are the same, instead of going through the point, it bounces on the point. So here's the value. So we've got x equals 0 here, and of course this is x plus 5, so it'll be x equals -5. Now, because it's positive, we're going to move through it. So what we're going to do is, so we'll start from here, start at the bottom, and instead of going through it, because then that'll be a mistake, because it's repeated, we bounce on it. So we'll be bouncing on this, and then curves upwards and then shoots up. That's it. Something like that. That's it. As long as you got the right kind of idea, it must bounce. It must not go through. If you had three distinct points, it'll go through one, go through another one, and then go across the final point. Simple as that. Okay, and yeah, that's it, I guess. Now, here's the main part of the question. So we've done this. So the points with coordinates -3 and 0, so when x is -3, y 0, lies on the curve with the following equation. Now just take a moment and realize that this equation is the same as the previous equations, except now that x has transformed into x plus a. Okay, so if we have to think about this, notice how when we factorized the previous equation, we had something like this, yeah? Factorizing gave us this. So just writing this neatly, our original factorized equation was just x and then x plus 5 squared, just to make it simple. Now we can just realize that because x is transformed to x plus a, just replace all your x's with x plus a. So that would be the new equation. So the new equation is going to be y equals, instead of x, we're going to have x plus a. And instead of this x, we have x plus a. So we have x plus a, and then of course, plus 5, all squared. Now we know that this point lies on this curve, so we just plug this coordinate into this equation here and find the two possible values of a. So I've already solved this as well. So scrolling down, I literally said at -3, 0 with the equation we just obtained over here. Plugging in x is -3, which I did, and y 0. This equation becomes -3 plus a, and this one here becomes -3 plus a plus 5. Now 5 minus 3 is 2, so that's why I got 2 there. Now we just solve, and we equate this to 0 because y is 0. So therefore, solving this, we're going to have -3 plus a equals 0, so a equals 3, and 2 plus a all squared equals 0, and well, this means a is -2. And that's it, two values of a right there. So yeah guys, if this video also helped, give me a like, and this question's again helping as always, give me a like and subscribe and share my videos to your buddies. Okay, 14. Ooh, so it looks like we're dealing with population now. Okay, so this one we have to kind of think geographically here with these kind of questions. Okay, so every time you got population style questions, think about what happens in real life. Okay, so let's go ahead and look at the text. So a town's population P is modeled by the equation P equals AB to the power T, where A and B are constants and T is the number of years since the population was first recorded. Make sure you guys note this down, especially T. The line L shown in figure 2, okay, straight line equation, illustrates the linear relationship between time and log 10 of population for the population over a period of 100 years. So this has just been recorded from time equals 0 up until some point into 100. So, and again, it looks like they're assuming the rest of it is constant. So this can actually go up to thousands of years, but of course, we don't know what can happen in 1,000 years. There could be wars and so forth. So population can change. Let's assume that we live in a piece of world and nothing changes. The line L meets the vertical axis at 0, 5. Okay, intersects at 5 and has an x coordinate 0. And the gradient of L is 1 over 200. So m equals 1 over 200. All right, so far so good. So write down an equation for the line L. So this is straightforward. This is y equals mx plus c, okay? So let's just note this down. We know the gradient is 1 over 200. We know what y is. It's actually the y-axis, so log 10p. And we know x is technically t. So we're left with log 10p equals the gradient, 1 over 200, times t. So we could just say t over 200. And it's y-intercept, well, it's easy. We can see it intercepts at the point 5, so plus 5. That's it. So this is pretty much our equation right there for A. Now B, find the value of A and the value of B. Okay, so this is referring to the P equals AB to the power T equation. Now this is fine because you can already see that the log equation has P here already. So we can just substitute the variable P for AB to the power T. So we can say, okay, I'm gonna make some space here. So we've got log 10 and we've got now AB to the power of T equals T over 200 plus 5. So we can just say, for example, just look at the coordinates. So we got 0, 5 already. And you can just pick anything, since you can just plug in any value for T, and then as long as it's between 0 and 100, and you should be fine. So let's go ahead and say, hey, what happens when T is 0? So when you get T is 0, what do we get? So we're going to be left with log 10 AB to the power 0. So B to the power 0 is 1, so we're just left with log 10A equals, and then this becomes 0 over 200, so it just becomes 0 plus 5, so 5. And therefore we can solve this one. So we can say, you know, using the log properties, if we keep A in this position and raise everything by 10, so it'd be A equals 10 to the power 5. Now this is just log transformations, yeah? To invert the log, all you have to do is take exponentials across. So the logs cancel out, and then 10 raises up and 5 goes up. Think of it as a ladder case. You got A equals 10 and then 5 here. That's how I see it as a ladder case. So that's good. So that's one value, so 10 to the power 5. Now we got that. Let's see. We can also find value B. Now what I would do for this one, I mean, I would just pick something easy. I'll say, you know, let T be 1 or something, because it's linear and you can pick anything on this line. So let's say, okay, when T equals 1, what do we get? Okay, so we get log 10, and then now we know the value A is 10 to the power 5, 10 to the power 5, and then T is 1, so we're left with just B. So 10 to the power 5B. Okay, so far so good. Equals 1 over 200 plus 5. I'm going to go ahead and simplify that on my calculator. And doing that, I get, well, this looks kind of ugly actually. Okay, I'll go decimal. I'll go 5.005. Okay. Now, using the same idea, I'm going to use the log transformation. So I'm going to raise 10 up using the staircase method. So 10 goes up and 5.005 becomes a power. So doing over here, we should get 10 to the power 5b. That was in the bracket equals 10 to the power 5.005. Okay, not bad. Now finally, just to solve this one, just divide 10 to the power 5 across, and you're left with b equals 10 to the power 5.005 over 10 to the power 5. And doing that in your calculator, so you should get, I should have wrote this in. Now this one, I'm not sure they want it in exact form because they don't specify, but I got about 1.011. So I got roughly 1.01. Let's say 1.01, yeah, or 1.012. So 3 decimal places. You could also just subtract the powers if you want. You could say b equals, so 5.005 minus 5 is just 10 to the power of 0.005. Yeah, but that looks kind of ugly, so I'll stick with 1.012. That's it. Okay, part C now. So with reference to the model, interpret the value of A and B. Okay, so what this is talking about is from the P equals AB to power T model. Okay, so let's just note this down. Oops. Now, what actually helps when you write this down is the fact that you have the values now. So let's go ahead and plug the values in. We had A, which is 10 to the power 5, which is, in other words, 100,000 in the calculator. And B is simply some sort of multiplier, 1.012-ish, and to the power of T. Now, looking at this closely, if you see it specified, you can see that this is kind of like a compound interest formula, or a geometric sequence, basically. So we can say firstly that A seems to represent the initial population. So when time is 0, we get a value of 100,000. So A is always the initial population at time 0. So that's how it works. As for B, B represents a multiplier. So it's pretty much a multiplier of 1.2%. So if you just took off the 1.0, just took out the decimal bit, this is an increase of 1.2% per year. That's what we're working with. So the population is increasing by 1.2% per year. So that's all it is. So you can just write B is a multiplier which increases at this rate, whereas A is the initial population at time 0. And yeah, I put it down here as well, just to double check. Okay, part D now. So find the population predicted by the model when T is 100. Ooh, easy. Giving your answer to the nearest 100,000. So simply just plug in T equals 100 into our general population equation. So that means we're going to get P equals 100,000 times 1.012 to the power T. And when you get it, you should get about, I don't know, about 329 something thousand. Because we want nearest 100,000, it should be rounded down to 300,000. That's it, easy. So that's actually quite, quite generous when they give you a huge rounding figure. It's actually like very inaccurate, but cool. Now next one, find the number of years it takes the population to reach 200,000 according to the model. Okie dokie. So this one, well, you want to see when a population reaches 200k. So replace P with 200,000. So now the equation becomes 200,000 equals the general equation, which is AB power T, so 100,000 times the multiplier to the power T. And now we just solve for T. So here you can probably guess that we need to use logarithms. So I'm going to go ahead and write this down below. So let's go ahead and divide 100,000 across. So we get 2 equals the right hand side. So now we've got 2 equals 1.012 to the power T. Now to solve this one, just take logs on both sides. So taking logs on both sides, we get log 2 equals log 1.012 to the power T. Now thanks to the properties of log, the powers drops in front of the log term. So we've got log 2 equals T times log 1.012. And finally just divide log 0.1 blah blah across, and you should get T equals log 2 over log 1.012. Yeah, sorry, I sound a bit tired here because I've just been doing this non-stop. So yeah, so putting this in the calculator, and what do we get here? So you get log 2 over log. You can actually use the natural log as well, so you don't have to use this all the time. But anyway, this should take roughly, and this is to 1 dp, 58.1 years. Okay. And now finally, I just realized I missed a part. Now finally, looking back here, we still got part E. This is easy. So state 2 reasons why this may not be a realistic population model. In other words, we're looking at the straight line. If you remember in the beginning of this video, or the beginning of this question, sorry, we said that this is just a simple straight line model. So thinking about it carefully, we are assuming that this can go up for an unlimited period of time. So we're assuming a constant relationship. So we can't assume that the population growth is going to be proportional to the actual population size. Because as one population size increases, the growth may not necessarily, be proportional and going across in a straight line. So this is unrealistic because it also lasts for 100 years, and anything can happen in 100 years. There might be loads of hazards, for example, wars, famines, diseases, and this alone will affect the population growth. it may increase the death rate, so and reduce population births. So yeah, I just wrote a few answers which might be interesting, and I kind of looked at the math scheme just to see if they're in line with this. So I said population growth may not be proportional to population size. So again, it changes over time. More population may actually reduce the growth, or job opportunities may reduce it as well, and so forth, or any economical reason. The graph assumes unlimited growth, whilst ignoring possible fatalities. For example, fatalities. God. Example: wars, famine, nationwide disease, etc. So yeah, what we just said. And of course, 100 years is just a ridiculous long time. Yep, this is crazy. I mean, imagine we're talking about up to 2100, and there's a good chance, God forbid, we don't know how far we'll live. And in 100 years, we might not even, the countries that we live in today might not even be the same countries. Anyway, so that's it. That's really 14 done for you guys. So yeah, if you guys enjoyed this video, give me a like, a thumbs up, subscribe, and share with your buddies. But otherwise, I shall see you guys next time.